So I'm going to present the results of the use case 5 as obtained by the time of the SMIG workshop held in April this year. So in this use case 5, we were inspecting if the signal generated by a hammer could be used for seismic imaging of the surrounding rock. Such information can be very useful in drilling processes since it can help, for instance, to determine when to go from hammer drilling to core drilling. Also, geological interpretation of those seismic images can be very useful in planning and guiding drilling programs. Another goal was also to inspect if we can monitor the direction of the drill bit. That would help to understand whether the drilling is proceeding on the desired trajectory and adjust the drilling process to the desired trajectory already early during the drilling process. This would then help to reduce drilling risks and costs. Our field test was conducted last year in August at the Epiroc or near the Epiroc factory in Örebro. The location, this test site, as called test site, was part of the project IEDA Test Center financed by EIT Raw Materials. This place was very suitable for our experiment since it already was built basically or planned for testing new exploration drilling technologies, among them also seismic wire drilling systems, downhole geophysical methods, and similar. Also, the test site has previously been also surveyed with conventional geophysical methods, so our results could be then compared with those. So our test was done during the drilling of 200 meters deep borehole. And we were supposed to repeat the test, at the next drilling, but the funding was unfortunately cut, and we could not conduct another test, which would basically serve as an improved test in comparison to the first one in terms of acquisition setup and processing workflow. So this image shows how it looked like at the site. This was in Örebro, as I said, last year in August, and the diagram shows a drill bit depth versus time. So the survey or the drilling was performed during the 3 days period in August. This image here shows the acquisition setup. We had 45 active vertical geophones with a spacing of about 2 meters. The rig was located approximately in the middle of this profile, so it was close to the geophone 17. So I will show how the raw data look like. So here is this image shows the raw data, and you see that the highest noise is near the geophone 17, where the drill rig was placed. The reference signal of this geophone closest to the rig was used later for cross correlation with other recordings, so from other geophones, in order to obtain a seismic image that looks like an active seismic image, so more like a conventional result in conventional shot gather. It's called shot gather. I will talk about this soon. Usually how it's done is that there is an accelerometer installed on top drive of the rig, and that records the signature of the bit, but that we did not have access to that, so we had to use an alternative approach, which is the nearest geophone. And our geophone, when I say this, is our receiver, our small device that detects vibrations. And therefore we basically proceeded with that approach. It's not at the moment really clear if this would provide equally good or a worse image. We tested different processing workflows, we tested different parameters, and we ended up with the one shown here. There were some modeling indicated that, for example, spectral whitening in number 3 would provide better images, but the real data did not show a large improvement with that. Nevertheless, the results look still pretty good. This is just a glimpse. I will show now the full section of full section. When I say that means wide range of different depths. It goes from 12. You see it's marked here in the black square. So from 12, 18, 24, these are all depths of the drill bit. So every 6 meters. And as you can see, here you can maybe you will understand more what we are observing by looking at the result of the conventional seismic test. So the result of that, which was also partly interpreted when looking at the velocities here. For instance, this direct arrival, this part of the section, this was indicating that we have dry glacial sediments here, and then this refraction here, it's a water table refraction, water saturated glacial moraine, and this is about 2,700 meters, so something that we basically observe in our data everywhere. So this refraction of this water table refraction is well imaged in our seismic while drilling images. The modeling confirms our interpretation. However, as you can see, there is another arrival here in the active seismics. This is bedrock refraction of 5,500 meters. We don't observe it here, firstly, because we don't have a long enough profile for this arrival to come in, and secondly, even if we had, it's not really clear that we have high enough signal to noise ratio to observe that arrival. Maybe another thing that I should mention also is that since we had a very short profile, there was a large part of the profile was covered with drilling rig noise, and that was very hard to remove. So you see part of this data basically muted so that we could better focus on the arrivals that do represent the actual geology. This is deeper. These are drill bit depth of from 134 to 165 meters, and you see that we still have very good signal. The arrivals are consistent with the modeling result, and this velocity of 4,700 meters is the result of the depth of the drill bit. So most of the arrivals are in the bedrock, so that's why the velocity has increased. So conclusions, comparison of the real data with the modeling results shows an agreement. Besides the strong contamination by the rig noise, and the more typical for data that we have, it's more offsets. There are other issues that we had as a result of that, which definitely jeopardized a bit the quality of the signal. Nevertheless, the results still look good. The only thing is that we well image the refraction, water table refraction, but since active seismic also hasn't really detected any reflections deeper in the bedrock, we could not really fully inspect the quality of seismic signal generated by the hammer. Monitoring drill bit trajectory. This part of the job started with the modeling, and in this image you can see the approach. So the idea behind is that if the drill bit is inclined, then our receivers would detect changes in travel times. The processing goes in the same way as for seismic imaging. We have to use the reference trace, and we need to cross-correlate it or apply cross-coherence with other traces to get the active seismic image, or something that looks like active seismic image. Here you can see the results of this approach. So you have a no deviation in the left column with deviation in the right column, and you can see that it's actually pretty clear where this deviation in the drilling trajectory is happening. So, and it can be detected already at 2 meters depth. So it's really promising results. However, we need to keep in mind that the real data contain much larger noise, level of noise from the drill rig. So basically the real data test would give us maybe better insight into the capabilities of this approach. And this is now an ongoing process, so I hope we will get the results very soon. Nevertheless, the modeling results show very promising results and show very promising outcome that we may be able to monitor the deviation of a drill trajectory. And near real-time processing of the data would allow then a near real-time correction, which would be an excellent success. So, as I said, testing more realistic models is absolutely necessary, and as well as the real data processing. So these two together would give us a very better insight into the possibilities of the methodology. Okay, that is all, and I hope that we will get some good results, improved results very soon.